We wait for the message.
Yeah.
Think that we can prove like universe content covers all the subgraph. Yeah. So
Yes,
yes.
Okay, my name is Manuela. Ruiz-Montiel, you already know me. I'm here to make a short statement because well, I'm a computer scientist and I work with architectural projects, and so far I've only made studies in computer science groups, but I wanted to come to a more architecture-oriented group in order to exchange ideas and seek possible ways of collaboration. So as I have said, I'm a computer scientist. I've always had a passion for everything related to architecture. So when I started thinking about making a PhD, and I found a project in which computer science and architecture were connected, it was like perfect for me. This is the title of my thesis. New intelligent design techniques for architectural projects. And what I'm starting talking about my research group. We are in the University of Malaga. In the first photo, you can see our computer science school. And on the right, you can see a photo of all the members in my group. This photo was taken 5 years ago, so many of the people there are not anymore in the group. You can see me in the middle, and some of the people are still in the group. And we also work with some architects in the School of Architecture in Malaga, which is this building. They are the architects. Well, this is my advisor. He is another researcher in computer science, and the rest of the people are architects in the architecture school in Malaga. So this is the title of my thesis project. This is the exact title: New computational techniques for detecting, learning, and managing criteria in design programs. What is the goal of my work? I want to develop such techniques in order to help design practitioners by means of suggesting possible solution with a low level of detail that can somewhat trigger the creative leap or give some insight into the beginning of the project, of the process. So it's like the first phases of the design process, in the conceptual design phase of design. So far I have focused on architectural design. The methodologies we have developed would also apply to another fields of design, like furniture design, but we have only focused so far on architectural design. So in our methodology, we need three things. The first thing is a set of reduction rules, geometric rules that can give rise to different shapes. Also a design program, that is a set of guidelines that evaluate how a shape these are given a given set of criteria or requirements, and of course a means of controlling the production system, because we need to optimize the shapes that are produced by the production process. The production systems we have considered are mainly shape grammars. There you can see an example of a typical shape grammar in which you have emergence and you have a maximal line representation. But we have also used in some of our projects symbolic shape rules, in which we don't have that maximal line representation, and we just detect in a symbolic way which shapes are present. So with the same rule, we will have a different derivation. But in all of our projects, we have considered shape grammars or either symbolic shape rules. How we do control the production system? Depending on the nature of the production rules, we can talk about more naive rules in which no expert knowledge is codified inside the rules. So we just have rules made from scratch without an intention in these rules. Or maybe we can have more expert rules in which the designer has put more knowledge, more expert knowledge, hard-coded inside the rules. And depending on this, and also on the controlling method, I have used this scheme to classify our different approaches. In this axis, we have what I have talked about, that is the nature of the production system. In this part, we will have naive production systems in which the rules do not codify expert knowledge. And in this part, we will have expert production systems in which the rules do codify that expert knowledge. And in this vertical axis, we will have classify the methods for controlling that rules. In the lower part, we will have no automatic control, that is, we just would apply the rules randomly or with no automatic control. And in the upper part, we will have more sophisticated methods, like machine learning methods or some possible search algorithms. In this quadrant, we will have the so-called expert shape grammars, in the sense that that they do not need another means for controlling the execution. That they are the pure shape grammars as working by Stimian. And in our work, we have covered the rest of the parts. In this part, in which we have an AI production system, and so with more or less sophisticated automatic control, we have developed this work, which is with reinforcement learning, and is our main work because it is the main topic in which we have been working, because we are trying to develop new reinforcement learning techniques. But we have also experienced another methodologies that will fit in this quadrant, in which we have more expert production systems with some more or less sophisticated automatic control of the production rules. And even in this quadrant, who at the beginning may seem strange, because we have naive production rules and we have no control, but it's also interesting from a theoretical point of view, as we will see. So the first work I'm going to describe is the one naive production system with reinforcement learning, which fits in this quadrant. So as I have said, we use naive rules In this case, we don't use a pure shape grammar, we use symbolic rules because we don't have a maximal representation. With little expert knowledge codified inside the rules. That is, they are naive because they will produce absurd shapes if we do not control the execution of that shapes. That execution is controlled by a reinforcement method. And this method is used to decide which rules are better to apply to a given state, to a given shape. The problem we have tackled in this work is to design a housing unit according to a given housing program. Completely single-family housing units. The idea is that these schemes, which are very low detailed, will act as starting points or seeds for complete architectural projects. They are intended to trigger some creativity or to give ideas to designers who are starting to think about a possible single-family project. The housing program we have used is based on a proposal that a study of architects made for the region of Andalusia. The architects are Manuela and Ruiz. They are from Barcelona. Well, this is a little graphic brief about which is said inside this proposal. It has a lot of criteria that is not reflected in this diagram, but here you can see some relations that must be established between the different spaces of the house. For example, we have a complementary space that is like the distribution space that must be related to the non-specialist spaces that are, for example, the bedrooms or the living rooms, also to the bathroom and the entrance. Then we have the kitchen, which has to be related to a non-specialist space that would be, for example, the living. The other non-specialized space would be related to the bathroom because it will correspond to the bedroom. And also the entrance has to be more or less near the kitchen. And well, these relations are classified depending on if they are more necessary or less necessary. Then we have another requirements about space, about different space requirements of each type of space that are not reflected in this diagram, but we have still taken them into account. So, what are the production rules we have used in this system? We have used an additive approach, and we have used like we work with the small elements. For example, if we are going to add the kitchen, we work with the different modules of the kitchen. And we have tried to include the less possible expert knowledge inside these rules, but we have taken some elements from the housing program. For example, as they talk about a distribution space, in one room we place a distribution space. These first rules are aimed at generate the control of the housing unit. These rules, for example, are aimed at placing the kitchen, and you can see that we work with small squares of 60 centimeters of side, which is the type of modules the housing program talks about. We also have the bathroom modules, which are 90 and 1 meter and 90 centimeters side. This one is for the non-specialized spaces, and the last one is for the entrance. As you can see, there is a set of rules for every type of space that the housing program talks about. And we have tried to define these rules without having into account that requirements, because it would have led to a more expert shape round. We wanted the shape rules to be naive. So if we executed these shapes randomly, we wouldn't obtain good starting points because we have no means for controlling them. We also divided the generation process into phases. It is more or less depicted in this diagram because this is the first phase for the generation of the control. This one place is the distribution of space. This one place is the kitchen, the bathroom, the non-specialized space, and the entrance. So these are the different phases of the generation control. And as I have said, if we execute that rules randomly without extra control mechanism, we would obtain shapes that make no sense because we would have very scattered contours with the different ambits placed in an absurd way because they overlap. You cannot access, for example, the kitchen in this layout. They are not applicable at all. How do we manage to apply the previous rules in a way that the outcomes are good according to the housing program? For that, we use the reinforcement learning techniques. So now I'm going to talk about how reinforcement learning works. In reinforcement learning, we have two elements that are key to understand the technique, that are states and actions. A state is, in our context, is a shape. It is completely identified with a shape. And the action would be the different rule applications we can apply to a given shape. For example, if we have the shape map that I put at the beginning, in which we could add a second square to this one, we will have 4 possible rule applications that will correspond to 4 possible actions that I can apply. Okay, so what is the aim of our reinforcement learning agent? The purpose is to find a policy, that is to find a function that can tell us which action is better to take, that is, which rule is better to apply, and with which transformation in a given state, that is, to a given shape. For that, we use this scheme in which we have the agent, who will be the algorithm that is learning. At the beginning, he doesn't have any information about which action to take, so at the beginning, he could take a random action. Then the environment, in our case, would be like the rule interpreter, who would tell us which is the next state that we reach after applying that action, and also tell us another thing, that the S is the next state, that is the next shape, and another thing that tells us is the reward that we obtain. That is, it tells us how good is the shape that we have produced with that action. So we obtain the new state and the new reward, and now the agent performs another action. So the shape is grows as the rules are applied, and in the end we see what is the accumulated reward, what is the sum of the rewards I have been obtaining along the process. When I reach a final state, for example, if we are in the first phase of our generation process in which we generate the control, the final state, the final shape will be one with 46 square meters, because the housing program tells that the minimum size of a single family housing unit is of 46 square meters. So when we reach a final state, we will see which is the accumulated reward along the process, and according to that evaluation, we would see if the actions that we have taken out of the process are good or bad. If we repeat that process again and again, in the end, we will know for each state which actions lead to a good shape. Okay? If you have any questions at the moment, I can explain to you. Try. Because this is a little, yes.
I didn't get who teaches it what is good and what is bad?
That is the like an evaluation module that computes the report. It depends on the, for example, in our case, it depends on the phase we are. For example, if we are generating the contour, our measure of how good is a shape is the compactness factor. If the shape is compact. Depending on the phase, we will have a report or another.
Okay.
So it is the thing that I explained here. So as I have said, depending on the design program, we can have many different goals to specify. In our case, for example, we have spatial relationships, available space for different areas, accessibility, shape of the house, etc. So if these goals are satisfied in a shape, the reward is high, but if the goals are not satisfied, then we punish the shape with a low reward.
I have a question.
Yes.
Let's say you are in a state and you apply a rule.
And you?
Apply a rule. And then where does the reward get attached to the rule? How do you remember the reward?
You sum all the rewards obtained until you reach a final state. And then you use that number, that final sum, to decide if the actions you have already taken are good or bad. You wait until the end of the process.
Okay, so you start at the beginning, as usual, and you get to the end, and you get the reward. And then you assign that reward to each of rule applications.
It depends on the particular reinforcement learning algorithm you are using. But a general idea is that you retro-propagate that value to the different actions. So if you get a high reward, then the actions you have taken along that path take a good value.
Altogether?
Yes,
Not different
altogether.
from the last rule has the same value as the first rule.
Yes, altogether, but maybe in another experience, in another episode, it's different. So at the end, not every action is going to have the same value because it depends on the...
Do you weight rules?
Sorry?
Do rules have different weights? Like something is more important than something else?
It depends on the experience. Maybe if many good experiences use a particular action, that the rule corresponding to that action will have a biggest weight.
For instance, if you are at a state and you want to decide which rule to apply, you choose a rule that has attached the biggest reward.
Once you have finished the learning process, that is the number of experiences used to learn the value of each action, you don't use the reward anymore because the reward is like a short-term measure. You seek the long-term value, and what you learn during the process is a value for each action. So you store that value, and then you can use that value in order to decide which action to apply. So it's not. It's similar to the reward, but it's not the reward. It's what you learn after many episodes.
So, like Lilia was saying, some rules have a bigger weight attached to them.
A bigger value.
Yeah.
Yes, because they would lead to a better state.
Most likely, they will lead to a good solution.
Sorry?
most likely they would lead to the solution.
Yes, yes, but they are always attached to an state and an action. I mean, you learn a value,
Mhm.
it's like a function, which depends on the state on which you are and the action.
Okay, so you remember two things.
Yes,
State in which the rule was applied and how successful applying the rule at that state was in the past.
yes.
Okay, I understand.
Do you investigate a combination of rules, of actions actually? Maybe some combinations, two actions together?
Yes, I understand. No, we have only experienced
Steps
one,
Oh,
yes, step by step.
But it would be interesting.
Yes, it would be so interesting. Yes, to make some kind of clusters.
Yeah,
Yes.
between actions, because they usually, they probably won't learn that by the.
Mhm. It's a good idea.
Okay. Why these particular rules? Like you have shown in one slide that they are the rules. Yeah, these one. So why only these rules or why particular these rules?
I designed these rules because, well, they take into account the different elements of the mentioned in the housing program. They are naive because they don't have code expert knowledge inside them. So maybe we could have chosen another rules, but we experienced it.
And it guarantee that these rules somehow they will produce solutions.
Sorry?
So, like these rules guarantee that at the end you will have some good solutions.
With the reinforcement learning process. By themselves, they do not produce good solutions because if you execute them randomly, you get things like that.
Okay, so what those rules do is to add bits of qualified space.
Yes,
Okay, so a bit of kitchen, a bit of bathroom, and so on. Or a bit of wall,
yes. Mhm.
but it's very elemental.
Yes, yes.
Just one more portion of kitchen, just one more portion.
Mhm. They are by nature additive. They add the small pieces of the different elements that have to be.
You were saying that you use those guidelines for housing programs for the Junta de Andalucía.
Mhm.
So that means that you check certain things like the dimensions and of spaces
Mhm.
according to the guidelines.
Mhm. Yes, for example, the non-specialized space need a 3 diameter circle around the center in order to be habitable according to the housing program. That's just one example.
Good, thank you.
So we have once we have the value for each action and on every state learned, we can use that policy in order to decide which we are going to apply at each stage of the process. Some results with this policy, using this policy, are depicted in this slide. And you can see that they make more sense than the previous random outcomes, in which the control was very scattered and there was no way, for example, in this, the non-specific space was outside and among many other absurd things. In this slide, you can see that the shapes are better. Maybe they are not perfect, but they make some sense. Okay. So we conducted an experiment with architecture students in which we used this methodology to produce a lot of different starting points of different schemes. So we made groups of students and we gave like 100 schemes to each group, different schemes. And they had to classify them We are working on that because we need that to be very fast. Because we need to do a lot of experiences, a lot of episodes, and we need that the evaluation data software like Energy Plus it has to be very fast because if it is slow, like for example 5 seconds, the process will take a lot of time. So now we are working on that. For the moment, we are using a set of rules of thumb, and we are using a software similar to Energy Plus in order to validate the results. But we are not using the software as a part of the learning process.
May I just ask you a question?
Yes.
One of the things that I find interesting so far is that you are designing layouts that are basis of work for further development. What we have seen is that the students get those sketches of possible plans and they arrange them and combine them differently. So following this logic, this kind of evaluation doesn't make much sense because how can you evaluate the energy efficient of a possible plant that is going to be a part of a bigger one?
It will be, we will use the methodology for its isolated single family houses.
Because it might be,
yes,
one plant might be very efficient if it's isolated, but maybe inefficient if it's combined,
right.
or the opposite.
If you are going to combine them into a bigger layout, then it makes no sense.
Or even one that would have a very low reward with this kind of approach. If combined in a different manner, might get like the other one, the octagonal plant, that you have the gaps between them filled with the other spaces.
You will need that information. Yes. In this case, we will use the methodology to make just isolated housing units.
We call your attention to two things. One is the difference between energy sufficiency. Yes, and energy efficiency. That's a new distinction. By energy sufficiency, people mean design the house in such a way that you avoid using artificial means of climatization. Okay, so basically, the way a house is designed, or is designed in such a way that you don't need to have heating or air conditioning, heating in the winter and air conditioning in the summer. So that's the new term of sufficiency. So you design a house in such a way that you minimize the need for energy efficient solutions. So that's also a new trend in the European Union, the new guidelines regarding design of housing for this distinction. But in fact, in Portugal, we have had what we call a regulation on thermal comfort since 1990, in which sufficiency was the key concept. So they use rules of thumb, but in a mathematical format, meaning that they made very rough calculations to ensure that at the end you get a design that's as efficient as possible. So I think you have two ways to go from now. Either use the sufficiency concept, and for instance, use the Portuguese guidelines for that. It works very well in Southern Europe because we can design houses without the need for artificial systems, especially in Portugal and Andalusia because they are reference house. Or you could use something like Ecotech or a program like that to check the quality of the solutions. The difference is that for using something like Ecotech, you need to have a full solution. Whereas for the other one, you don't need that. You can start with sketches.
Yes, you can take some kind of decision about the material and the.
Well, basically what it says is if you use these construction solutions, you are guaranteed to have a satisfactory solution at the end. And then you try to optimize the layout and the design of the house to minimize the use of artificial systems. I can show you, it was just a thesis that I was reviewing last week
Okay.
in Porto with Vitorial. Okay, so I can give you a copy to you. It's quite interesting and it follows, the concerns that were described.
Okay. This is what we're doing now, and that was the methodology with naive production system and more or less sophisticated means for controlling the rules, that is reinforcement learning. And now I want to talk about, yes?
Sorry, just the last question.
Yes, of course.
So you're teaching the rules by some kind of parameter that should be optimized, right?
The
So, for
report.
example, in contour, you should have maximum compactness.
Yes.
Would it be possible or interesting or something to have humans evaluated? For example, you produce a series of solutions, and then you give to the human and say, I like this.
It will be very, very interesting, but it will be slow, because in an reinforcement learning framework, you need a lot of episodes.
How many?
We're working about
Thousands?
Yes, thousands. And this is even.
Okay, so
Hundreds of
So it will be very interesting because we will have also the human touch in the sense that, for example, aesthetics that are very difficult to measure it without.
even if it's not aesthetics, sometimes it's difficult to hard code certain things because we don't really know how we evaluate it. So obviously it's interesting to understand why do we evaluate it like this. But for example, in your case, maybe that's not the point. The point is to get an optimal solution. And maybe, of course, if you have 100 students evaluating solutions, maybe it's too slow. But I was recently reading a paper that was also asking humans to rank qualities on some things. In this case, it was on shapes like dinosaurs and stuff. What they used was mechanical Turk, which is something like it's like a survey, an online survey, and you send it throughout the world, and then you collect the answers. So maybe you get the thousands of answers that you need in a relatively short time.
Yeah, it's very interesting. I also read a lot about genetic algorithms that use
Yes, that's
human
also-
evaluation. And maybe in genetic algorithms you need less iterations in order to get a good result, and it's suitable to have human evaluations. But maybe if we develop a new algorithm that needs less experience to learn, we could use some
Yes.
kind of human evaluation. It would be very interesting.
How fast you can manage to create a schema?
Once you have learned the value, 1 minute.
If you're doing like 1,000 of them, okay. I was thinking about how fast you get.
And how fast is the learning?
The learning is about maybe 1 hour per phase.
First phase.
Yes. Yes, it depends on the phase, but on average, 1 hour. That's a bit understanding. I can tell you later.
No. That's approximate.
Okay. So I have already finished with reinforcement learning, and now I'm going to talk about another experience which fits into another part of this scheme, which is that one in which we have a more expert production system, and also we have some kind of automatic control. But in this case, we don't have focused on a particular problem, because what we have done is a tool, a software tool for architects and design practitioners in general. So we consider more expert production rules because this software allows to define general shape grammas and also allows to implement means for controlling the execution of the shape gramma. This method is just adding design constraints and goals, which are considered inside our tracking algorithm. So we will see now in detail how it works. The software is implemented as a plugin for SketchUp. It allows to create, edit, and execute shape grammas, and it also allows to work with layers. We have somewhat extended the concept of shape grammas to layered shape grammas, in which we have different layers of shapes, and if we manage to define layers with few points and maximal lines, we can even reduce the execution time of a shape gramma. And also, inside this software tool, the user can define different design constraints and goals by means of a wizard, and even if the user has programming skills, even he or she can write a little piece of code in order to check if a given shape complies a constraint or goal. You can download the tool from this page. I think design is here.
Yeah.
Okay. It has also a manual user guide. I think you could use. I don't know. Maybe it works with the previous version of the SketchUp. But if you manage to install it in the new version,
Version last version of the previous, like still Google one?
the Google one, yes, but I think that it can be installed in the
New one.
new one. So this is a screenshot of the software. In the left part, we have the shape rules. In this case, we only have the default one. In the right part, we have the current shape that is being generated, that is shape gramma. Then we have a lot of toolbars that can be used to add more rules, to add constraints, add goals. Well, you can do a lot of things. You can use different commands in order to apply the different rules. It's a standard shape gramma interpreter, but it has the additional feature of the layers, which you can see in this small window, and also the constraints and goals. So what are constraints and goals? They are just conditions that can be evaluated to true or false. And they can refer to different aspects of the design that we are generating. For example, it can refer to the labels that are present in the shape. They can refer to the time, the number, the position. They also can refer to the maximum lines of the shape. The user can also restrict the type of rule transformation that he or she wants to apply. For example, if you want to prevent a rule transformation that involves scaling, in which the rule is applied bigger, then you can prevent it or always force to be applied. And you also can impose, for example, a rule ordering. In fact, the possibilities are limitless because as you always can code directly what you want, you can check a lot of different aspects of a shape. There is also a technical guide for the tool in order to learn the different programming interfaces you need to use in order to implement a constraint algorithm. But you also have a wizard in which the more common constraints or goals that you may want to consider inside a shape, they are predefined. So, for example, if you have a goal in which you want that in your shape you can find a number of squares, you would keep on, the software would apply rules until the goal is complied. I don't know how many squares are inside this shape. Let's say it's 10. So you imagine that your goal is to have 10 squares inside the shape. And your constraints, you only have one constraint in this case, that is that you cannot have a maximal line that is bigger than 1 meter. So for example, these two shapes do not comply with the constraint because they have one maximal line that is 2 meters long. This also happens the same. This is okay, but it doesn't have 10 squares inside it, and you have to apply one more rule until fulfilling the goal. It is a toy example just to see how it works. Okay, it is a backtracking algorithm. If you reach a state which does not comply with goals and you cannot keep on applying actions, then you backtrack and keep on searching another solution. This process is made automatically by the software. So we use the software just for illustration purposes with two toy examples. The first one was aimed at producing housing schemes following a methodology that the Spanish architect developed, which is based on L modules. They are called L because the shape of the modules are like the L letter, but with an H. And the different, there are different constraints about the proximity, the spatial relationships between the different spaces. For example, we have a dining room that has to be near the kitchen, which is this one. So with different constraints and goals and a more or less expert shape grammar, we managed to do these schemes that are really straightforward, but it's an example of what can be done with this software tool. Another example was to create restaurant layouts for video games. I don't know if you know the typical Facebook video games with restaurants in which you have to construct a restaurant and then you have to put on furniture to cook different dishes and everything. So looking at the different types of layouts, we developed a shape grammar, more or less experts, and with different constraints and goals, like the number of tables, the number of chairs, the space between tables, for example. We managed to produce this kind of layouts. The good thing about this software is, as it works with layers, we can associate each layer with a different height. So in the end, you can visualize the results in 3D dimensions. I have not put it here because it was very long, the presentation, but I can show you. But I think I have it. These are the same, and then you can see it in 3D. Then you can put materials with Google SketchUp, and it's like very beautiful. That the shape grammar is in 2 dimensions. The third dimension is just associated with each layer. So that's the work with more or less expert shape grammars and constraints and goals. As I have said, it's just a software, and the examples we have made are just toy examples. We haven't focused on a serious design problem. And the last work we have done is fits in this part of the scheme. In which we have an AI production system, and we don't have an automatic control. It may look absurd because if our shapes are naive and we have no control, then the rules are going to produce always absurd shapes. But we wanted to study to what extent designers or architectural students completely explore randomness when they use a system of this nature. So our idea was to study if randomness can serve as a source of inspiration. The users using this system can as well manually control the production of the shapes by controlling how rules are applied, the number of rules that are applied, etc. There is another SketchUp plugin, I think that you can also download it on the same page. And the goal of the experiment we conducted is to see if architecture students could generate megastructures using the random commands and the control commands. And well, here you can see a screenshot of the tool. We have a 3D, in this case, it is a three-dimensional production system. It is not a shape programmer because it does not allow emergence, it's just symbolic. And the rules are all of them additive. So the students have to produce some kind of megastructure from a metabolic point of view, just by adding little cells. They have some commands that were aimed at controlling manually the production, and some other that were more random, where I meant at producing random shapes. So there are two different results produced by the students. This one is totally controlled, and I think that the students get inspiration from an existing building. I don't know which building it is, but I think that it exists somewhere. And this one is almost completely random. So we wanted to see how good were the different designs produced by the students, and to what extent randomness was used to produce that designs. The conclusions were that the students were willing to explore randomness. The majority of them, of the students, prefer designs in which randomness was used to a certain extent, but it's not the same for the preferences of the teacher. The teacher, when evaluating the shapes, although randomness was present in many of the best qualified designs, in the end, the teacher showed the preference for more control. So it was just a study, a theoretical study about this kind of randomness, and how random can inspire the students. So far, well, until this point, this is my work, in which I have been working since I started with my PhD. I'm here to present my thesis, maybe after summer. And now I'm going to talk very briefly about what we do in my group. The name of my group is Investigation and Application of Artificial Intelligence. I need to be very brief. What historically we have done is to develop search algorithms, mainly with Wikipedia, in which we have into account a lot of different conditions to fulfill. We are now developing applications of those algorithms, collaborating with some companies, mainly in road design problems. Okay, to design roads according to a certain terrain features, and also optimization of fast routes in order to make them faster and more efficient. These are the names of the projects. The one of the road design is the GATE project, and HELA project for the bus.
It's road design, more
specifically what the design of the street itself, what how it is connecting.
Sincerely, I don't know because I'm not in that project, but I think it has to do with the design of the
It's not
road.
streets, it's roads.
Oh, yeah.
So it's
Sorry.
in the countryside, outside urban areas.
Sorry?
Road means it's not a
Outside,
street.
yeah.
It's outside
yes.
urban area.
So it's more about the connections.
No, about topography, you know.
Yeah.
I really don't know because it is a project in which I'm not involved at all, but I just know it's like highway design, taking into account the features of the terrain of the floor in which that roads are going to be. And the bus routes depends on the city and the number of lines that you want to work. And well, the present and hopefully the future of our work is also reinforcement learning, because so far in my group the work has focused on exact search algorithms that do not allow to deal with very big state spaces or uncertainty, because they just when you take an action you always read an action. But reinforcement learning does allows also dealing with uncertainty as well as with bigger state spaces, applying some additional techniques. Well, this is more or less the work that we are doing, and that's all.
Well,
Thank you very much.
well, thank you very much for the presentation. I think it was quite good. It was very clear, and the work that you presented is very much connected to what we do here, although using different, slightly different approach, like the use of reinforcement algorithms, learning algorithms, which is refreshing for us, so that we get to see other ways of doing things. And I think it would be very interesting if we could come up with something, some sort of collaboration, because you are mainly computer scientists, and you are mainly architects and mathematicians now, which is good to make the bridge between the two. Let's see, I think it could apply to some European funding to develop a project along these lines. So what the important thing is to find a very clear project with a very clear goal. And you can, do some brainstorming during lunch today to see what could it be.
Okay.
Any more questions from the audience?
Do you have a plugin for the other thing that you showed about the design through accumulation of cells?
Sorry,
Do you have a plugin available for the second?
for the random,
Yeah.
yes, but maybe it's not. I think apart from the larger shape random one, there is another plugin that you can download, but I don't know if it's the one for the randomness control. I have to check it, but I can give you a link to the code.
The first argument we remember the feedback.
Yes.
Is it about in Ruby on SketchUp or not?
In Ruby.
In Ruby?
Yes.
But they did for SketchUp also. It's just,
No, I have used Ruby because I was comfortable with it, and you can, the algorithm is executed outside the interpreter of SketchUp because it is kind of slow.
you developed Ruby and you execute the code, whereas I don't know, I never used Ruby, actually, I'm not comfortable with it. But we did this kind of interface that allow you to prompt the design.
You mean to program the?
Yeah, the program is to output your what you done, like generating a solution in C.
But you mean the API of the plugin, of the Google SketchUp?
I was thinking, you show some design for the first
Yes.
time, and you generate them where the design were
Oh,
complete.
well, they were generated using SketchUp.
Ah, okay.
Yeah, the learning algorithm is executed outside, but once we have learned the policy, we use SketchUp in order to interpret the rules
Yeah, and prompt.
and visualize.
Okay. I was thinking it was mainly also the learning process was kind of I don't think it was prompting
No.
the execution of that. Also the add-ons,
Yes.
just
For the visualization, we always use SketchUp.
yeah. I think that's the problem. They want to see something. Also, is wrong.
I have one more comment. I think that in the first case, it is very interesting that you use naive rules, and then at the end you get very interesting designs, because I'm talking as an architect. So the plans that were output by the system are very interesting from an architectural viewpoint. So I will be interested in learning more about the rewarding system that you use on each stage of the generation process. So that this leads me to another question. It would be wonderful if you could give us some of your papers and your thesis
Of course.
for us to read. But I think I mentioned this already yesterday. This idea of naive rules with controlling mechanism that is equivalent to an expert grammar, because I think it would be possible to develop an expert grammar for the outcomes of your naive control system, which I think it would be very interesting to do that as a way of comparing
Yes.
the way
Yes,
knowledge
it's
is
very
encoded.
interesting to see. Yes.
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 More questions?
No, I really like the basis of your work, in which you are not trying to provide final solutions, but guidelines. And then from the same guidelines, different solutions emerge. Some of them that were not confined to, actually all of them were not confined to the boundaries of the diagram that you provided. So there were different arrangements with that. And I find that very, very interesting in the design phase. Of course, there is always a temptation to, okay, what if I just move a little bit of, I change the diagram a little bit, but that's good also because you provide the basis for that to happen. So, and it has structured basis. And so it's very, very interesting. I'm not so confident about the other point of the energy efficiency that I already pointed out, because it has to do with the final design and not the basis. And I don't know if that would be of course it's interesting that you're doing it. How can you give another constraint to the rule, especially if you just want to make, for instance, if that would be the diagram for a single family house. It's isolated, it's that diagram, you might have something, but that's it, stabilized. But when you, sorry, yeah. No, when you start building something larger from that, it kind of loses the point. Because you are adding other constraints that will never be evaluated, and you're probably discarding some design layouts that might be interesting.
Yes, when it comes to energy efficiency, there is a lot of variables that we are not having to account, and it's very difficult that we are trying. We just, I think we started the project like 2 months ago, so it's very first development part. Yeah.
But no, it's very nice because I already have the feeling of, okay, opening SketchUp, downloading the plugin, okay, let's play with this. And is it possible to edit and create new rules within the plugin?
With the second one, the one of the layer check grammars,
but then can you use those rules in the previous, in the first one?
No, it's not integrated. You mean with the reinforcement learning approach?
Yeah.
No, it's not possible. We are planning to in the future.
Because that would be an interesting step you
Yes,
know, as a progression of the work.
yes,
Because then you would have, okay, these rules are nice for this kind of data science, but I want more. And
yes,
designers always
it will
want
be
more.
very interesting. We would have to study a lot about the interface because we will need a lot of parameters of the algorithm and a lot of customization.
Yeah.
So it will require a lot of study of how
Yeah.
the interface will be developed.
Thank you.
And it's just, I am really happy that you are addressing the value in architecture. A value, the question of value. Value?
Value of
Role in architectural design, because it is something that we usually don't address because it's tricky to approach. And I think that is the, I see it as the main core of your work. But whichever value we think about, it can be energetic efficiency or something else, or accessibility, whichever it is. I think the process is really important. How we can understand which actions or which design brings value. And you said that you were investigating some previous houses, some existing houses.
Well, for the reinforcement approach, we just started from the housing program and we didn't study any existing buildings or houses.
Because maybe through investigation of existing architecture, it has some intrinsic, stable, continuous values, so you can find some.
Yes. It could be interesting to find another production rules and also consider another evaluation system.
See if there is similarity between different cultures.
Yes, of course, and the guideline we have been using is confined to the region of Andalusia.
Yeah. No, it is great because this is the beginning. Congratulations.
Thank you.
Okay, thank you all for coming.
Thank you for your attention.
Thank you.